We define a spanning tree to be a subtree of an underlying graph that follows the guidelines of being a tree. So just to recap trees from the last video, recall that a tree is just a minimally connected graph. Basically, if we have a set of vertices, say 5 or 10, a tree is going to be the way of connecting up with a bunch of edges in a minimal way, which one of the main properties of a tree is it always must have n minus 1 edges. And so basically, when we're looking at a lot of graphs, like say for example looking at the graph on the left, this graph is clearly not a tree because it violates all of the criteria. It has too many edges. If we were to count, well, we have 1, 2, 3, 4, 5 vertices. This definitely has more than 4 edges. It has circuits. There's more than one path between the 2 points. So anyways, it fails all of the conditions of being a tree. But aside from that, there is a way to use some of the edges from the graph that are present to actually form a what we call a spanning tree. Basically, a underlying tree in the graph where we're using some of the edges that it has to manufacture a tree. So again, given that this has 5 edges, a tree must have n minus 1. Sorry, it has 5 vertices. A tree must have n minus 1 edges to it, where in this case n is 5. So if we were looking for how many edges would be in a tree, it must be 4. And like to the right, you can see I've given one example of what we call a spanning tree, which is just basically taking some of the edges to form a tree. And notice that we have 1, 2, 3, 4 edges in this particular spanning tree. And if you're wondering, well, how did I pick these edges to form a spanning tree? Well, that's the issue is there are numerous ways to formulate spanning trees between them. And we could invent them just by basically trying to connect the dots in a minimal way, however we want to. So that example on the right is one example of a spanning tree of the graph. And in graphs, there's often many different possibilities for spanning trees. Like for example, I could just pick edges at random, like let's say this edge, and this edge, and this edge, and this edge. That would be an entirely different spanning tree. And the way that you know it's a spanning tree is, well, it has to connect all of the vertices together. Because if it's not completely covering the network, right? Because again, what we can imagine in these sorts of problems is we're trying to build power lines or water lines or railroads, and the goal is to make sure everything is connected. All the points are connected to each other. Like, if I'm imagining these are power lines and I've now just figured out which power lines I could build, you could imagine the yellow as now electricity flowing between those, and all of our towns, all of the dots now would have power under this configuration. But the configuration on the right would be another totally valid configuration as well to make sure all of the cities get power. And this is exactly what we're going to be working towards in section 7.3 is what we call a minimum or maximum spanning tree. Because the question is, how do we discern between this solution with the 4 yellow edges or this solution, which is the right one? Because if we don't have numbers or other factors, well, there's lots of different spanning trees that are possible. And our goal, like in the very original problem, was to figure out a way to build the power lines that would cost the least money. And that's, there's a pretty simple algorithm for doing that and finding the spanning tree. But basically, there are a lot of different possibilities for spanning trees in general. And when we have a higher redundancy, and just to review as well, redundancy is the term for meaning how many edges too many does a graph have. Like if we're looking at this graph, we can see that we're using 4 edges in a spanning tree. Every other edge would be redundant, basically. So we'd have 1, 2, we could just count the non-highlighted edges to figure out, well, what's the redundancy? 1, 2, 3, 4, 5, I believe. Or you could just use the formula, which is take the actual edges in this graph, which I believe there's 10, and subtract from how many edges there should be 4, which is actually 6. So 1, 2, 3, 4, 5. Well, actually, I didn't actually count the edges, so if I was to be very careful, we could go count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It does look like there's 10 edges here, so the redundancy should be 6. It looks like I am not counting one. So let me do this again. 1, 2, 3, 4, 5, 6. Yes. So redundancy is 6 here. And be careful when you are when you're calculating redundancy, because when there's a lot of edges, like in a graph like this, there's a lot of overlap, and it can, can be very easy to miscount. Or one way I suggest doing it is you can draw the graph and mark it with a little colored pencil or a line where you can kind of tell, okay, I'm actually counting properly. Um, and anyways, but yeah, so our goal in this chapter is to find what we call an optimal spanning tree. Basically, of all of the different spanning tree options which we may have, which is the best one. And we, of course, we need numbers, because if we don't have numbers, well, who's to know which of these is better? I don't know. And the goal is to typically find what we call a minimum spanning tree, or as the book says for shorthand, MST, where that's just spanning for minimum. But basically, it's just a tree which has the minimum net weight or the minimum net cost. So if we can imagine all of these edges having numbers to them, whichever of the options, when we add up all the numbers, is going to be the cheapest option, would be our minimum spanning tree, which again we can't do without numbers, but you can kind of imagine, um, between these different hypothetical solutions, they're using different edges, so of course they're going to have different weights. And find, using all of the, and obviously we want to use the smallest numbers, that we can in order to actually configure a spanning tree. And then in the same exact fashion, a maximum spanning tree or max ST. Unfortunately, min and max both start with M, so this shorthand that the book uses is a little bit not great in my opinion. But just warning you, MST is for minimum. That's typically what we're finding. But you could also apply the algorithm the same way to find a maximized spanning tree, which would just be finding whichever one of these trees of all the options has the greatest sum weight at the end of the day.